Page 238. Lesson 4.5 is linear approximation. In Unit 2, we looked briefly at the idea of local linearity. When zooming in on a function, we discovered as we zoom in, the straight line that appears at a given point has a slope equal to the derivative, and the equation for the tangent line was defined. Okay, so this f of x equals f of a plus f prime of a times x minus a. That is basically your point slope line there. Okay, we go deeper here. So tangent line approximation. Suppose f is a differentiable function at point A, then the values of x near A, the tangent line, and they give this same approximation, folks. We'll realize f of x is another way to say y. F of a is like y1, plus f prime of a is another way to say slope, times x minus, I guess I'll say x1 or x of a, which way did it, yeah. So that same equation we've used, right? It's our, you guys are probably used to saying seeing y1 at the end though, maybe? Or do we usually put it at the front? I don't even remember at this point. Do we put it at the end? Okay, and here's the deal. Officially, does it matter? No. And you need to get comfortable looking at it either way. Okay. So we define this expression, the second part of it, as the local linearization factor of f near the point x equals a. And I'm going to just read through this real quick because it'll make more sense when we start doing examples. Okay. If you consider the point A is a fixed point, then f of a and f prime of a are constants. So that is your y value and your slope. Now, this piece we already have here, right? F of a plus f prime of a, x minus a. It's defined as L of x. L of x standing for the linear approximation. And it's just the idea, guys, what this is all going with. When you have a curve, right? You have a tangent line. Tangent line hits that curve at a point. That tangent line is what we use to approximate the slope of the curve in that area. Okay? That's what we're looking at. Okay, that's our linear approximation here. We are also going to talk about linear approximation error. You'll be asked to find some error. And the error in the linear approximation is just the gap between the actual curve and the tangent line. Okay, how far apart is it? You know, at that point of tangency, it's real close. The farther away you get from that point of tangency, the farther the error becomes. Error can be calculated as the exact minus the approximation. You see delta f minus f prime of a times delta x there. They also talk about percentage error, which, if I recall, we don't do a lot with that, but it's the exact minus the approximation divided by the exact, and then turning it to a percent, so multiplying by 100. Okay? So those are the pieces that we're going to kind of look at. I want to use this graph. I'm going to make it a little bit bigger here so we can see it. You can see what I write and point at. Get rid of those pieces. So we have a graph here that represents, and it can be shown that the best linear approximation to f near A is the tangent line approximation. They asked us to label a couple of things. Label the true value of f of x, the tangent line, and the approximation. Okay, so realizing you have your curve, yes? So when we start talking about our curve, this is what we would refer to as f of x. If we're finding a value on that curve, then the value on that curve is going to be your exact value, or your, what do they call it, the true value. Okay. So, for instance, this point, or more importantly, this point is what I'm going to talk about. This is your exact value, or your true value. Okay, because that is f of x. That is, when you plug in whatever x is, that is the exact value at that point that's on the curve. Now, where's my tangent line? Tangent line is this straight line, yes? So there is my tangent line. That is our tangent line to the curve at point A. Okay. If we are at, so the tangent line is at the point A, we can use this tangent line to estimate values close to A. So if you're now asked for x, the true value or the exact value is here on the curve. Where's the estimation? The estimation is that point right there. Okay, that is your estimation or linear approximation value is the vocabulary I used. Because that's what they use here. Okay, so this point right here represents the linear approximation value because it's on that line and it's approximation of the values on the curve. Remembering, the farther away we get from A, the less of a good approximation it is. Okay? Approximation, f of x, tangent line. You will notice e of x here. And if you looked up above, e of x represented the error. Okay, so e of x, and I don't know if you can tell here, but it is this gap between the 2 points, and that is your error. Error being the difference between the exact value and the approximation. Okay. Now, we've talked about underestimates and overestimates before at some point. Yes? And I remember talking about them. But my question here for you, and they don't ask it here, but I'm kind of prepping us for later stuff. Is this linear approximation value an overestimate or underestimate? Under. Why? Okay, it's under the true exact value, yes?
Yeah, it's under the slope of the graph.
Okay, and here's the deal, okay, to generalize it more, I mean, you can see obviously it's under, but here's the deal. Where is the tangent line in relation to the curve? The tangent line is under, right? So all of these values are going to be underestimates. The other thing to take into consideration is that this curve is concave up. Okay, so it's always going to be an underestimate when your tangent line is below and you have a concave up curve. Okay? Yeah, underestimate since the graph is concave up and tangent line is below the provided graph. So I don't know if you want to put a note about that or not, but underestimate, I can't spell, since tangent line is below graph and graph is concave up. Okay. The key is you don't always have a picture to look at, which is why we're talking about the whole idea of the graph being concave up and the tangent line being below it. It's obvious in here, yeah, it's an underestimate, but we don't always have that graph to look at. Okay? Okay.
Yeah, it's a lot.
It is a lot, but okay. Let's spend a few minutes here looking at the procedure. And again, the procedure, we'll practice it. Okay, it's going to make some more sense once you practice. So if your head is spinning with this new information, Let's summarize what we'll be focused upon for the remainder of this lesson. When you need to write a linear approximation for f of x, centered at a given value, say x equals c, and you need to approximate f of x at a value that is in the neighborhood, let's call this new value x of a, then proceed as follows. First of all, we're going to write a point slope equation for the tangent line. So basically we're going to write the tangent line. Usually when we write our point slope, we already have y isolated, but isolate it, and we're going to rename this as L of x. That is your linear approximation. We'll substitute the value that we're using in the equation for L of x. This will be an approximation of f of x. If you need to explain whether or not the approximation is an over or underestimate, consider the behavior of the function in your neighborhood. Is the function concave up or concave down? Because basically if it's concave up, that tangent line is always going to be below. If it's concave down, your tangent line is always going to be above. Okay, so if you know the concavity there, which we talk more about in the next chapter, in chapter 5, but concavity relates directly to the second derivative. Okay, and then some of them they'll ask about error. When finding the error or accuracy in an approximation, use your calculator. Okay, find the absolute value of the difference between the exact and your approximation. The error should be stated as being less than 10 to the negative p. So basically like scientific notation, because that error should be very, very small. Okay, where p is the number of zeros in your result. For example, the error is less than 10 to the negative third would be reported for an error such as 0.000147, because we're 3 zeros off from the decimal there. Okay, and then if you need to find percentage of error, there's the formula. Let's work on 2. But let's get it so it's writable and readable. So example 2. The function f is twice differentiable. We're given that f of 3 is negative 2, f prime of 3 equals 5, and f double prime of 3 equals 1. Write the equation of the tangent line. Then use the equation to find the value of 3.1. Okay. What does f of 3 equals negative 2 mean?
3 at the value at x equals 3, y is equal to 2. Yeah.
Okay. Or how about, so the value at x equals 3 is negative 2, so we have the point 3 negative 2. Remember, that's just a fancy calculus way. I don't know that the calculus is ever going to say, here's the ordered pair 3, 2. They're going to say f of 3 equals 2. Okay? What does f prime of 3 equals 5 mean?
At x equals 3, nice.
Okay. So here they're giving you the slope, specifically the slope at the point 3, right? So at that point above, the slope, if you want, I could say m equals 5. F double prime of 3 is 1.
Acceleration.
What you do know about second derivatives, acceleration. Really, it kind of talks about concavity, but in this scenario, it's not necessary. So I have written down that it's extra. I was trying to see if we could connect it. But I don't think I have a connection. So I just have that f double prime of 3 equals 1 is extra. Okay. So write the equation of the tangent line, then use the equation to find f of 3.1. So if you go back up up top in this or up to the previous page. Okay, they give you f of x is approximately L of x, which equals f of a plus f prime of a times x minus a. That's the fancy version, right? But we've got to be able to understand the fancy version too. Okay. What are we using for a?
3.
Yeah, because all the information they're giving us here is about 3, yes? So a is 3. So when we go, okay, we're writing this equation, f of x, which is approximately equal to L of x. F of a, what is f of a? F of 3, but what is f of 3? Negative 2. Plus f prime of a. The slope at 3, which is 5, times x minus a.
X minus 3.
X minus 3. Now, if you prefer, maybe you would have preferred to have said 5 times x minus 3 minus 2. Would that have been better? That's what you know, isn't it? Because what did we just do? We did slope of 5, and then the point 3, negative 2.
Huh. That makes sense.
I'm teaching you what you already know. Okay? So, and you guys know enough at this point in your math careers that you can reorder things. You don't have to write it exactly in their order. Okay? So, I see people that put the minus 2 last. I see people that put the minus 2 first. Your pick. Okay. So, what we have right here, that is your equation of the tangent line, right? We took the slope and the point. We wrote the equation of the tangent line. Now, what did they ask me to do?
Find the value.
Find the value of f of 3.1. So it's f of 3.1, which is approximately equal to L of 3.1. What are we doing? Putting in 3.1. Which, before you grab for the calculators, I will say this math is doable without the calculator. Okay? Because when they give you these, you could see this without a calculator. 3.1 minus 3.1. So then you're doing 5 times 0.1. 5 times 0.1?
0.5.
0.5.
That makes sense.
0.5 minus 2.
-1.
You could do that with a calculator, without a calculator if you had to, right? And I'm not saying that's the direction you have to go. I'm just saying that when they have that subtraction, you're getting like a decimal of 0.1, they might do that. Okay? So this is f of 3.1. Yikes. Is approximately the negative 1.5. Okay? Now, okay. No, that's what I was just trying to decide. Now, keep in mind, the actual at f of the on the graph f at 3, the value is -2. Yes.
Yeah.
What are we saying? On the tangent line, it's negative 1.5.
So it's above.
So it's close-ish, right? It's close-ish, close-ish, blah, but not precise. Okay, and that's what our approximation will do this. Now, linear approximations do a great job of estimating values for f of x, provided you stay in the small neighborhood. closer you are to A, the more exact. The farther we move from A, the worse the approximation becomes. There's no easy method to determine how near or far away we can move. We can predict the error to give us an idea of how good the approximation models the actual value. And then it says, let's look at a famous linear approximation used to describe vibrations. Pendulum motion is used as a method to supply formulas in optics, which is sine. So, yeah, there's no, I mean, I could start trying to go into it, but I think it'd be better if I just stopped there. And we'll pick up there tomorrow. Now, we have lots to get through tomorrow then, but.
We got 1, 2, 3 pages. Can you use, or, we got one day to do